Welcome back. Let's prove this theorem. If M be a closed linear subspace of a Hilbert space H, let X does not belong to M but X belongs to H. Let D be the distance from X to M. Then there exists a unique vector Y0 in M such that norm of X minus Y0 is equal to D. By the definition of D is the distance from X to M, norm of X minus Y such that Y belongs to M, or we can say D is less than or equal to norm of X minus Y. Okay, now from here we can see that there exists a sequence Yn in M such that norm of X minus Yn tends to D, or we can say that limit of X minus Yn is equal to D. Now we consider two elements of the sequence. Consider Yn, Ym belong to M. Then Yn plus Ym divided by 2 belongs to M. Since M is a subspace. Now, by the definition of D, we have D is less than or equal to X minus Yn plus Ym divided by 2, or this can be written as 4D square is less than or equal to twice of X minus Yn plus Ym norm squared, or this can be written as 4D square minus X minus Yn plus X minus Ym squared is less than or equal to 0. Okay. Now, by the law of parallelogram, we have norm of X minus Yn plus X minus Ym squared plus norm of X minus Yn minus X minus Ym squared is equal to twice of norm of X minus Yn squared plus norm of X minus Ym squared. Okay, and now this can be written as, from here it is norm of Ym minus Yn squared is equal to twice of, we can replace norm of X minus Ym squared and norm of X minus Ym squared by D as n tends to infinity. Now, this can be written as norm of Ym minus Yn squared is equal to 4d square minus norm of x minus yn plus x minus ym squared, and from third it is less than or equal to 0. So we can write ym minus yn squared is less than or equal to 0, but we know that norm of ym minus yn squared is always greater than or equal to 0. This implies we can write ym minus yn squared is equal to 0, or norm of ym minus yn is equal to 0 as m comma n times 2. Therefore, we can say that the sequence yn is a Cauchy sequence, and since M is complete, because M is the closed subspace of H, M is a closed subspace of H, therefore M is complete, and hence the sequence yn must converge to some point y0 in M such that limit of yn is equal to y0. Okay, so now from x minus y0, we have x minus limit of yn, or this can be written as norm of x limit of x minus yn, or again it is limit of n tends to infinity norm of x minus yn, and from second is equal to d. So we have proved that norm of x minus y0 is equal to d. Right? Now we have to prove that y0 is unique. To prove that y0 is unique, if possible, let y0 comma y1 belong to M such that norm of x minus y0 is equal to d, and norm of x minus y1 is also equal to d. Now again we have y0 comma y1 in M, therefore y0 plus y1 divided by 2 is also in M, since M is a subspace. Therefore, by the definition of D is less than or equal to x minus y0 plus y1 divided by 2, or this can be written as 4d square is less than or equal to x minus y0 plus x minus y1 squared, or 4t squared minus norm of x minus y naught plus y1 squared is less than or equal to 0. Now, using law of parallelogram, we have norm of x minus y naught plus x minus y1 squared plus norm of x minus y naught minus x minus y1 squared is equal to twice of norm of x minus y naught plus norm of x minus y1. Okay, so both are squared. Now, this implies norm of y1 minus y naught squared is equal to twice of, we can replace these two norms by d. So it is d squared plus d squared minus norm of x minus y naught plus x minus y1 squared, and this can be written as y1 minus y naught squared is equal to 4d squared minus norm of x minus y naught plus x minus y1 squared, and again it is less than or equal to 0. So we can say that norm of y1 minus y naught is less than or equal to 0, but norm of y1 minus y naught is greater than or equal to 0. So this implies norm of y1 minus y naught squared is equal to 0, or we can say norm of y1 minus y naught is equal to 0, or y1 is equal to y naught. So y naught is unique. The theorem is proved. Let's come to next theorem. In this theorem, we have M is a proper closed subspace of a Hilbert space H. Then there exists a non-zero vector Z0 in H such that Z0 is perpendicular to M. If M is a proper closed subspace of H, this implies X belongs to H, but X does not belong to M. Now let D be the distance from X to M. Then D is in favor of such that Y belongs to M, or we can say D is less than or equal to norm of X minus Y. Now, according to the previous theorem, if M is a closed subspace of H, then there exists a unique vector y0 in M such that norm of X minus y0 is equal to D. Since M is a closed subspace of H, then there exists a unique vector y0 in M such that norm of x minus y0 is equal to d. Now, if we assume x minus y0 is equal to z0, then norm of z0 is equal to d. 1 and here it is 2. Now, x comma y0 belong to H implies x minus y0 is also equal to z0 belongs to H. Now, to prove that z0 is perpendicular to M, okay? Now, let y belongs to M and alpha be any scalar. Then y0 plus alpha y belongs to M. Since M is a subspace. Now, by the definition of D, we have D is less than or equal to norm of x minus y0 plus alpha y, or this can be written as x minus y0 minus alpha y. Again, we can write norm of x minus y0 as z0. So it is z0 minus alpha y. Okay. Now, squaring both sides. Or this can be written as inner product of z0 minus alpha y comma z0 minus alpha y is greater than or equal to d square, or we can say norm of z0 square. Now, we can write inner product of z0 comma z0, or we can say z0 comma z0 minus alpha y minus alpha, and here it is y comma z0 minus alpha y is greater than or equal to norm of z0 squared, and this can be written as inner product of z0 comma z0 minus alpha bar inner product of z0 comma y minus alpha y comma z0 plus alpha multiplied by alpha bar, and it is inner product of y comma y, and this can be written as norm of z0 squared is greater than or equal to 0. Now, it is also z0 comma z0 minus alpha z0 comma y minus alpha. This can be written as z0 comma y conjugate plus alpha alpha bar, and it is norm of y squared minus inner product of z0 comma z0 is equal to 0. Now we have this term minus alpha bar inner product of z naught comma y minus alpha inner product of z naught comma y conjugate plus alpha multiplied by alpha bar. Now y squared is greater than or equal to 0. Now this relation is true for all values of alpha. So we consider alpha as beta multiplied by inner product of z naught comma y, where beta is a real number. Therefore, we can find alpha bar, it is beta z naught comma y conjugate. Now, putting the values of alpha and alpha bar in 3. Here, alpha bar can be written as beta inner product of z naught comma y multiplied by z naught comma y conjugate minus alpha, so it is minus beta inner product of z naught comma y multiplied by z naught comma y conjugate plus alpha multiplied by alpha bar, so it is beta squared and multiplied by z naught comma y conjugate square is greater than or equal to 0. This can be written as minus twice of beta and inner product of z naught comma y squared plus beta squared and again z naught comma y squared. Now y squared greater than or equal to 0. Now we can take beta multiplied by mod of inner product of z naught comma y squared common, and here it is beta now y squared minus 2 is greater than or equal to 0. Now let us assume that inner product of z naught comma y is non-zero and beta is positive and so small that beta multiplied by log y squared minus 2 is less than 0. Okay, so if we put this value in 4, so we get beta it will be less than 0, which is a contradiction of 4th. So therefore contradicts. Fourth, therefore, we must have inner product of z naught comma y equal to 0. Or we can say that z naught is perpendicular to 1 for all y m. Now we can write z naught is perpendicular to m. Okay, the theorem is proved. See you in